Programming, the backbone of our digital world, powers everything from websites, games, to AI chatbots. Before we start learning it, we need to answer a fundamental question. What is programming? A program is a set of instructions that tells a computer what to do. However, computers don't understand human languages, so we use code, their special language, to communicate with them. Just as people use languages like English, Spanish, or Chinese to communicate across the world, programmers use different programming languages for various areas in the digital world, such as JavaScript for websites, C# for games, and Python for data and AI. Each language has its own syntax, the grammatical rules for writing code, but the core logic structuring instructions to solve problems is universal. Think of syntax as the language of a book and logic as its story. The story is what matters most, right? So this tutorial will focus on logic, making it easier to learn language's syntax once you master it. An important declarement is that all code syntax in this tutorial will be based on Java with several adjustments for better explanation. So some code might cause error when running on real Java programs, but again, focus more on logic, not syntax. Without further ado, let's buckle up and start our journey. Program is a set of instructions for a computer. But how do we use code to communicate with them? For example, to calculate 7 plus 6, we use code like add 7, 6. To subtract them, we write subtract 7, 6. By using different keywords, we make the computer perform different tasks. Each instruction in programming is called a function. Similar to mathematical functions, the input are called parameters, and output is the return value. Think of a function as a tiny machine. You feed it ingredients, it processes them, and it produces a result. Each function has a name to identify it. Unlike math where inputs and outputs are typically numbers, programming functions handles various data types. Here are a few. First, numbers are definitely accessible. Programmers split them into two types, integers and decimals. In programming, decimals are often called floating point numbers. So in short form, int represents integers and float for floating point numbers. Text in programming, whether a single character, word, or sentence, is called a string. Strings are enclosed in quotation marks to distinguish them from other code elements like variable names, which we'll cover in the next chapter. Computers use binary, ones and zeros, and we represent this as Boolean values, true or false. Booleans, shortened to bool, are key for decision-making code. We'll use them in the third chapter. One special thing to mention: some programming functions perform actions without returning a value, like a print function displaying text on the screen, but don't return anything tangible. In programming, we say their return value is none or void. There are more data types like vectors, enumerations, and colors, but these are enough to get started. Let's apply our knowledge to build a simple calculator app. First, let's use an add function to sum up two numbers. To show the result on the screen, we use the print function, passing the add function's return as its parameter. To get user's input, we use an input function which waits for keyboard input and has no parameters since the input comes from the user. Features like subtraction, multiplication, and division work similarly, just swap the core function. Because calculation functions are fundamental to computers, most programming languages use math-like symbols for calculations. This looks different from a typical function, where parameters are placed after the function name, but they're still function at heart. Don't let the syntax fool you, the logic remains the same. Okay, a quick wrap-up. A program is a set of instructions. Each instruction is called a function. To use a function, we use keyword to identify it. We pass the inputs, the parameters, after the keyword, and it produces an output, the return value. The input and output can have different data types like numbers, binary, and text. A special data type for functions that performs actions instead of a value is none or void. And some function looks different just to simplify the syntax. Our Chapter 1 calculator app adds two numbers, but real calculators handle multiple numbers sequentially. How? Let's explore. For the first two numbers, we display the result directly. For the third number, the calculator uses the previous result. This process supports any number of inputs. This relies on memory, where computers store data. Memory is like labeled boxes, each with a unique memory address, a number that locates it. Since multiple programs share the computer's memory, we need to allocate specific boxes for our programming, using variables, named references to memory locations. They are like labels, making it easy to store and retrieve data without dealing with complicated addresses. There are 4 different operations towards variables. First, we can create a variable, use the keyword like var with a variable name, and we can use the set function to store an initial value. The set function often uses the equal sign to simplify. However, in most cases, a variable can only store values of a specific data type to prevent errors, so we often specify the data type in advance for clarity. To update a variable, we also use the set function. Next, to read a variable, we use the get function. We often call the variable name directly to access the value instead. Last, the memory will free up automatically when the program ends. Now let's operate our calculator app. First, we create a variable to store the result. We set it to the sum of 2 inputs. To add a third number, we retrieve the current value of the result and update it. Finally, we use the print function to display our result. We can also repeat and modify our set function to handle more operations. Remember here, result equal to itself assigns a new value, not equality. Unlike variables, constants retain their initial value, improving readability and prevent changes. So consider making a constant by using the const keyword if a variable's value stays the same the whole time, like game settings or website root, so it is actually very useful. To wrap up, variables and constants enable computer to store memories and manage data, powering sequential calculations in our calculator app. We can create, read, update, and delete them using different functions. Note that don't mix the set function with equal in math. Same symbol, different meanings. Our calculator app still needs to handle different operations based on user input, requiring conditional logic to choose the correct code. A condition is an expression evaluating to true or false, a boolean, acting as a decision point. For example, if the user enters plus, the program adds numbers. Otherwise, it checks other operations like minus and times, or else it must be division. Conditions often use a boolean functions to represent, like an equality function to check if 2 values are the same, with a double equal sign for comparison to distinguish it from the set function. For conditional logic, we can use the if-else statement. It evaluates conditions in order and runs the first block where the condition is true. If none are true, the else block runs. Conditional logic is not hard to understand, but are you curious about how this logic actually works? Let's use a fun example to understand. Consider a trip to Disney. You only bring an umbrella if the weather is rainy. In other words, you skip or jump this action if the condition is not true. Here, a new function jump if not come to rescue. It lets the program jump to a certain position only if the boolean parameter is false. This function has another parameter to record the destination by its line number or using a label. Here, let's use an arrow for better visualization. Instead of doing nothing without rain, if it's sunny, we also want to bring sunglasses. Otherwise, we only bring a cup. To achieve this, we can use the jump if not function again after the first condition is false. Here's the problem. The program will also run the else block even if the condition is true. So we add a pure jump function without any condition at the end of each block, jumping to the end of the conditional statement. This is an example when the weather is sunny. Note that in high-level languages, the jump function is deprecated. However, its logic is still reflected in conditional statements. A switch statement is an alternative to if-else statements when checking a single variable against multiple fixed values. Each option is a case, and the default case handles other inputs. This is often more readable. Like the jump functions we used, here we name them break, meaning to break out the switch to avoid running extra code. Wrap up time. Conditional logic enables programs to make decisions, powering our calculator's ability to handle user-selected operations. Conditions often use Boolean functions to represent, and the conditional logic can use the if-else statement. This logic actually uses the jump function to achieve. By using this logic, a switch statement simplifies checking a variable against multiple values, using case for each option and default for others. A break function exits the switch to prevent extra code execution. Tired of calculators? Let's switch gears and build a Wordle game, where players guess a 5-letter word in 6 tries. Wordle has 4 simple rules. First, your guess must be a 5-letter English word from a valid word list. After each guess, the game shows the color of each letter. If you guess the secret word correctly, you win. But if you run out of guesses, you lose. Let's start with the first rule. First, we can capture the player's guess in a variable. We can validate it with a Boolean function. If invalid, we give the user another chance to input. But what if they enter something invalid again? We need a way to keep asking until they give a valid word, while it's time to learn a new programming concept, the loop. In the last chapter, we discovered the secret of conditional logic is the jump function. Now, instead of skipping to the next few lines, if you jump back to the previous lines, it forms a loop, like buying a ticket multiple times. But most loops should have an end, meaning they only repeat while a condition is true. We call this a while loop. We can use the while keyword to use it. Let's apply the while loop to our game by replacing the if statement. Here, we notice the same set function. To improve readability, we can use the do keyword in the beginning, creating a do while loop. The code inside runs at least once, then repeats until the condition is false. This is how it works using jump functions. About the second rule, color the hint, we can do it by using a single function, color the hint. But I'll explain how this function actually works in the next chapter. For the win condition, we can use an equality function to check if the guess matches the answer. If it does, the player wins. And for the lose condition, we limited the guess to 6. This brings us to loops again. To control the number of guesses, we can use a variable to count how many times we've already repeated. After each round, we increase the variable by 1. The increase function often uses the double plus sign to represent adding 1 to the variable, so the loop continues as long as the repeat count hasn't reached 6 yet. This logic is often called by another name the for loop, since it repeats for a certain number of times. We use the for keyword with 3 components: initialization, which runs once before the loop, the condition, which tells when to end the loop, and update, which runs at the end of each cycle. Programmers often use I, J, or K as counter names. But if the player gets the answer early, similar to switch statement, we can use the break function to jump out of the current loop immediately. After the loop, we check if the player lost by using the non-equal function, which uses exclamation mark with the equal sign to represent. Now, our game is finished. The code seems a bit long, but it follows clear logic. We use the do while loop to get a valid guess, using a single function to color the hint, use an equal to function to check the win condition, and a for loop to check the lose condition. And now we unlock the logic of loops, allowing us to repeat a block of code multiple times. With condition, it creates a while loop. To run it at least once, use do while loop. To run it for a certain number of times, use for loop. And to break out the loop in advance, still use the break function. In addition, in this chapter, we found out that creating projects is a fantastic way to reinforce our knowledge and gain new skills. And just like we handle the rule one by one, breaking down a big problem into smaller, manageable parts make it much easier to solve. Let's complete our Wordle game by validating guesses and coloring the hints correctly. To validate a guess against a word list, we first need a way to store a list. A list is like a mathematical sequence, an ordered collection of numbers that can be repeated. Each number has an index to show its position. For example, to get a 4th number, we use a sequence name A with index 4. Similarly, an array in programming is an ordered collection of elements, like a row of boxes, each holding a value of the same type. Each element has an index starting at 0. Why 0, not 1? Actually, an array is a series of variable or constant stored in contiguous memory. When creating an array, the array's first element will be stored at the memory space address, and indices represent offset from that address, so 0 means no offset. This convention aligns with how memory is addressed in low-level programming, where the offset is added to the base address without needing to adjust for one base index. This tradition has been passed down to the present day. Array operations are similar to variables, creating it with its data type, update it using the set function, call its name with indices to access the value, and delete it when the program ends. For our game, to check a guess, we create a custom array word list of valid words. We loop through it using a for loop. Here, the length of function returns how many elements in the array has. Then, we compare each element to the guess. If a match is found, the guess is valid and we stop looping. We can store the result in a Boolean variable. One more thing to mention, just like an array, a way to store and organize data, we call this whole thing a data structure. Think of it like a toolbox. It holds data and provides rules for accessing or changing it. There are many more data structures to explore, but don't feel pressure to learn them all right away. You can pick them up as you need them. Next, for Wordle's hint, let's see the detail rule. A green tail indicates the letter is in the correct position within the word. The yellow tail means the letter is not in the correct position but still exists within the word. The gray tail shows the letter is absent from the word. Let's first determine if the position is correct. A word is a sequence of characters, so it is an array. To check if a letter is in the correct position, we compare the guess and the answer at the same index. If they are the same, we color the tile green. Next, to check if a letter in the guess is in the answer word, we need to track which letters appear in the answer. We can create an array of 26 Boolean elements, initially false, to mark each letter's presence. For each letter in the answer, we mark its corresponding index as true. However, array indices are integers, so we need a number-character mapping. This is where ASCII comes in. American Standard Code for Information Interchange, or ASCII, is a standard code that assigns a number to each character. For example, uppercase A to Z is 65 to 90, and lowercase is 97 to 122. Since Wordle typically uses uppercase letters, we'll focus on uppercase A to Z, which is 65 to 90. To map a letter to an array index, we subtract 65 from its ASCII value. To check if a letter in the guess is in the answer, we simply check the corresponding element's statement. If it's true, the tile is yellow. Otherwise, it's gray. Now let's combine our logic. If a tile is green, we need to skip the yellow-gray logic, ensuring each tiles get one color. Instead of using the break function to jump out of the loop, we use the continue function, skipping the rest of the current iteration and move to the next one, while the updating function continues. This is the full code of the checking process. So, this is array, ordered sequences of data. Enable our Wordle game to validate guesses. String, as a sequence of characters, is also an array. By using ASCII, we can map in characters to corresponding indexes, starting at 0. Also, we learned the new continue function. Unlike break function, it just skips the current cycle instead of the whole loop. Please keep in mind, like an array, a way to store and organize data is a data structure. This concept will help us to discover the secret in the next chapter. It's easy to forget what a certain part of code does over time, but by using the function, we can make code reusable and organized. Let's explore how to create our own function. Take its valid function as an example. We'll use the keyword like function, followed by the function name and parameters. Similar to variables, we indicate the parameters and return values data type for clarity. Then, we can use the parameters just like variables. We can reuse our code we wrote last chapter and replace the guess variable with word to match the parameter name. For the return value, as it's named, we use the return function to return the result back. To make the code neat, a good practice is to store the return value in a variable. Remember, the parameter and return value are both optional. When there's no return value, the data type void is used. You might wonder if more than one function in your code have variables with the same name will be a conflict. Actually, every new variable you create inside a function, including parameters, is like a little secret that only that function knows. We call them local variables, and they'll be deleted after the function ends. On the other hand, variables that are created outside a function are called global variables, and they are like the common sense that can be used in any function and the main part of your code. Since they are so important, it's best to give them a unique name so they don't get confused. Comments are another handy way to help us. Every programming language has a special syntax to create a single line or multi-line comment. The code after or between them will be ignored by the computer. They're also super helpful when you share your code with others. They explain code without affecting it. It makes their life easier. If we think of a function as an instruction book that we can read, then we can treat a module as a library that houses all these functions. For a small project like ours, we usually don't build our own modules. But hey, we can always borrow books from other big libraries. For instance, if we want to use more advanced math functions, we can import the math module. Once we've imported the module, we can use the function inside it by modulename.functionname. Like the abs function gets the absolute or positive value of the specific number. Besides functions, modules can also store constants, just like math module contains mathematical constants like Euler's number and pi. The syntax to access them is alike. While module contains reusable functions and constants, a class, on the other hand, is a blueprint for creating reusable objects, which could contain constants, variables, and functions. For example, in Super Mario Bros., a player class contains its data like his name, max speed, jump height, lives, and position. Some of them stay the same during the game, creating constants, while other variables change over time. It also contains an action a player can do, like move forward, jump, and lose life. However, we can't use the data now since the class is just a blueprint. We need to create an object, the actual instance of the class. That's where the constructor function comes in. Remember, every class should have this function to create a new object with initial values. Now we can create Mario and Luigi! By using the class, we can store and organize data easily. Wait, store and organize data. Sounds familiar? It's the same feature of data structure. Actually, nearly all data structures are classes. Array, for example, the length of function is actually written like arrayname.length because it's one of the functions that belongs to the array class. Besides, strings are also arrays, so they are actually classes too. For instance, to get how many characters are in the string, we can also use the length function. So learn the concept of class. Let us find the true appearance of programming, the combination of functions and memories. Function, module, and classes organize code for reuse and clarity. Smaller tips like comments and global local variables help us understand code better. Last but not least, the relationship between data structure and class is unbreakable. Our journey through programming's wonderland is coming to an end. Let's have a quick recap of what we learned. A program is a set of instructions. It contains two main parts, functions and memories. A function is a reusable chunk of code which help us deliver the instructions. Thanks to the jump function, conditional logic and loop logic are possible. We can also define our own functions and use functions from imported modules. Variables and constants are two kinds of name reference to a specific memory location. We can use get or set functions to retrieve or modify data easily. By combining functions and memories, a sequence of variables or constants creates an array. Just like an array, a way to store and organize data is a data structure. Data structures and string both belong to a class, the blueprint of objects they created. Okay, so what's next? Remember at first why you choose to learn programming. You want to make a game to share with your best friend, build your dream website and shock everyone, or just build a useful automation software to help you get football tickets because your hand speed is too slow. Well, don't hesitate, start your project now. But what else do you need to prepare for your project? Remember at the beginning of this tutorial, we discussed the core logic of programming, structuring instructions to solve problems. For each problem-solving method, we call it an algorithm, a set of instructions and logic that solves a certain question. For example, to find the guessing word from the word list is a searching algorithm. Toggle with the search option to get the most relevant result list, which uses sorting algorithms. To let the ghost chase Pac-Man, pathfinding algorithm is the secret weapon. So learning other algorithms towards common problems is actually very useful for your projects too. However, you don't need to learn them all before you start your project. You can learn them when you need them. To solve a problem, there are tons of algorithms. Which one is the best? Well, the first criteria is the time complexity, which means the time it consumes to solve the problem. We want the time as low as possible. Besides time consumption, space complexity is also important. This tells us how many memory spaces we need to use. We also want space usage as low as possible, but sometimes it might be in conflict with time complexity. Nowadays, computers have a lot of storage, so we usually focus on the time complexity more. One thing to keep in mind is that time and space aren't the only thing to consider. The logic complexity is still very important. As the quote says, any fool can write code that a computer can understand. Good programmers write code that humans can understand. Another useful skill is debugging. No one can excel on the first try. One handy way to debug is by using the print function to print out relevant variables. This allows us to keep track of the data and identify any issues. For instance, in the example provided, the counter I remains at 0 infinitely. Oh, the increase function is missing. Silly me. So, this is finally the end of a sense of programming. I'm so glad you've been following along. In the future episodes, I'll create a spin-off of this tutorial. Take a closer look at the key concept we've discovered. If you want to review and test your knowledge, related material is in the video description. Thanks again for watching. Goodbye.